Hello guys, good morning. You are welcome to my YouTube channel, the Explicit Tutorials. Please, as you are watching this video, endeavor to subscribe, like, share, and comment. In today's video, or before I get started, if you know you haven't watched the part 1 and 2 of this topic, State of Matter in Chemistry, I would advise you do so before watching the part 3 of the topic, which is going to be done right now, all right? Because if you don't watch part 1 and part 2, you may get confused, right? Because we are already running off. Okay, this should be the part 3 of the video. Then in our subsequent classes, we'll be taking some questions, some examinatory questions on that is right here. We'll be solving them on the board, all right? So, part 3. In part 3 of this topic, we have 3 laws. Is it 3 now or 4? We have Gay-Lussac's law. We have Gay-Lussac's law of combining volume. Now, Gay-Lussac stated a law called Gay-Lussac, that is a law called law of combining what volume. You therefore say Gay-Lussac's law of combining volume. This law states that when the volume is measured, at constant temperature and pressure, the volume of the gaseous reactants, and products in a chemical reaction can be expressed in ratios. Gay-Lussac's law of combining volume states that when the volume is measured at constant temperature and pressure, the volume of the gaseous reactants, and products in a chemical reaction can be expressed in ratios. Now, what does that tell you? It means that Avogadro's law is based on gases. What did I say? Gay-Lussac's law is based on what? Gases. It is based on gases, and in order to express these gases, number of moles are also included. All right, you know that in a reactant reactant and product have certain number of moles in order to balance the left and the right hand side of the chemical equation. Now, for example, during the industrial preparation of ammonia, ammonia of course is a gas, that is NH3. The catalyst used is finely divided ion. Now, what is a catalyst? Catalyst is a substance that alters the rate of chemical reaction. Catalyst is a substance that alters the rate of a chemical reaction, and at the end of the reaction, it remains unchanged. It does not change at the end of the reaction. For it to alter a chemical reaction, it means it either increases the rate of the chemical reaction or decreases the rate of the chemical reaction. We have two types of catalysts. Catalysts that increases the rate of chemical reaction are called positive catalysts. All right, while the ones that decreases the rate of chemical reaction are called what? Negative catalysts. So in the industrial preparation of ammonia, the catalyst used is what? Finely divided ion, and they use a process called Haber process. Haber process is used to prepare ammonia. Contact process is used to prepare tetra orthosulfate-6 acid. Frac process is used to extract sulfur from from under the ground. Oswald process is used to manufacture HNO3. Birch process is used to manufacture hydrogen gas. You have different processes associated with the manufacturing or synthesizing of chemicals in different industries. Okay, now for ammonia to be produced being a gas, two elements are actually involved. All right, nitrogen gas would react with hydrogen gas to produce what? Ammonia gas, which is what? NH3. This equation is not balanced. Don't forget your finely divided ion is included. I have 2H, I have 3H, I have 2N, and I have just 1N. I have to balance the chemical reaction. In order for me to balance the chemical reaction, we have to start including figures. And these figures are called what? Number of moles. I'll put 2 at the back of this place, and that it means that I now have 2N here. Automatically, this 2N balances this one here. However, hydrogen is not balanced yet. 2 times 3 is what? 6. And I have 2 I have 2 here. And we have to place 3 at the back of this H. That makes it what? 6. It means I have 6 atoms. I have 2, that is 2 atoms of hydrogen, but 2 moles of what? Hydrogen. Alright? So, based on Gay-Lussac's law, which expresses the moles, that is, it expresses the moles in the form of what? Ratio. How many moles do we have here? 1. How many moles do we have here? 3. You do not say 6. You don't say 2 times 3 is 6. No. The moles are actually the one at the back of the elements or products. Alright? Then, how many moles do we have here? 2. So it means that Haber process, during preparation of ammonia industrially, we have ratio 3 to ratio 1 to ratio 3 to ratio 2. And this confirms Gay-Lussac's law. Another instance is the reaction between sulfur and oxygen. The reaction between sulfur and oxygen to produce, okay? Sulfur is solid, sorry. Sulfur is a yellow solid, so we cannot bring it into it. So it means that if nitrogen gas should react with oxygen gas, I'll be having what? NO. It is not NO2, it is NO, which is what? Nitrogen 2 oxide. This equation is not balanced. What do? We have to balance it. In doing that, I have 2 here. It means I'll simply put 2 at the back of this place. So this becomes 1 to ratio 1 to ratio what? 2. So that is what you have it to be. Gay-Lussac's law expresses the moles of reactants to their products using what? Ratios. You see, that is what I just stated. So please take note of that. The second law we'll be taking right now is Dalton's law of partial pressure. Dalton's law. Dalton's law of partial pressure. And this was done in year 1811. Alright, so this law states that the total pressure exerted by non-reactive gases. The key word there is what? This law states that the total pressure exerted by non-reactive gas, alright? That is, okay, let me put it this way. This law states that the total pressure exerted by a mixture of non-reactive gases. Yeah, that is the word. Dalton's law of partial pressure states that The total pressure exerted by a mixture of non-reactive gases is equals to the sum of the individual gases that make up the mixture. The total pressure exerted by a mixture of non-reactive gases is equals to the sum of the individual gases that make up the mixture. It is simple. It is simple. Look at it here. What this means is we said total pressure, right? Of a mixture of non-reactive gases. It means that PT is equals, let me assume the pressure of these non-reactive gases as A, B, and C, or D, as the case may be. Then on that note, it becomes PA plus PB plus PC plus PD, so on and so forth. It means that the total pressure exerted by these gases is equals the total pressure exerted by these gases is equals to the sum of the individual gases that make up the mixture. That is all about this law. It means that PT is equals gas A plus gas B plus gas C plus gas D. Alright, so let me expatiate more on it. I believe it is clear enough now. Let me derive some formulas. From ideal gas as we expressed or established in our initial class, we see that ideal gas is denoted as PV equals what? nRT. nRT. I want to make P, which is the total pressure, as my subject formula. So it means over V over what? V. This will go into V. So which means that PA is equals NA RT over volume. This is also equals PB, right? Equals NB RT over V. Isn't that correct? It means that PC is equals NC RT over V. PD equals ND RT over V. So this is what you have it to be. The pressure of what? The gases, the various what? Gases. Alright? So that is what you have it to be. Alright? The total pressure exerted by the mixture of gases is equals to the sum of the individual gases that make up the mixture. Simple. And that can be expressed as what I did initially. I said that PT is equals PA plus PB plus PC plus what? PD. And this is what I have here. So please, it is very, very simple, alright? The next law is, I believe this is clear enough. The next law is called Graham's law of diffusion theory. Graham's law of what? Diffusion. His full name is Thomas Graham. That is his full name. And he said the law of diffusion in state of what? Matter. What did he say? He said that the rate of diffusion of gases at constant temperature and pressure is inversely proportional to the vapor density, to the square root of the density of vapor density. I'll take it again. Graham's law of diffusion states that the rate of gases at constant temperature and pressure is inversely proportional to the square roots of the density of vapor density, as the case may be. This is what Graham's law of diffusion. If I want to express this, and if I were to eliminate this proportionality sign, I will introduce a constant k, and this means t, k, then this will get out. It means that rd, as r square root d, equals what? K. It means that r1, the square root of d1, equals r2, the square root of what? d2. Don't you think so? Yeah. So I have this. I want to take rate to one side and density to one side. It means I'll divide this by this. It means that r1 divided by r2 is equals the square root of d1 over the square root of what? d2. Alright, so this is equation 1 under Graham's law of what? Diffusion. This equation what? 1. Another equation that can be deduced in this law is, rate is given as volume over what? Time. Volume over time. Rate becomes V over T divided by volume over T. If I should introduce times, what happens? The T will go up and the V will come down. Therefore, R becomes V1 T1 times V2 T2. You are not to cancel out. Therefore, it means that R is equals this times this. There's a mistake here. That is V T1 V1. It means that V1 T1, then T2 V2. Right, so V1 times this, so that's V1 T2 over T1 V2. Which means that in place of arrow this and this, I'll just put this. Alright, to write it, that becomes V1 T2 over T1 V2 equals the square root of density 1 over the square root of what? Density 2. This equation what? 2. So equation 1 and what? Equation 2. That is for that. The next one, we are still deducing formula. We are not done. So I'll rub off this part. Let me rub off this part. But we said that rate is inverse proportional to what? The square root of what? The density. And you know that density is what? Mass over what? Volume. Mass over volume. Now, from our ideal gas law, we see that PV is equals what? nRT. If I should make V the subject formula, that becomes nRT over what? P. Which means wherever I see V, I'll put what? nRT over what? P. Density is equals mass over nRT over what? P. And this will give you D as, this will give you M over nRT times P over what? 1. And this will be MP over nRT, equation what? 3. Very easy. Now you've gotten equation 3 as this. Now what do you do next? You also agree with me that N, which means number of moles, is given as what? Mass, small letter m over molar mass, big letter M. Which means that density is equals MP over M over big letter M times what? Times RT. This M will cancel out this small letter m, small letter m, small letter m. So from here, it means that D is equals is equals P over RT times what? Big letter what? M. Therefore, D is equals what? MP, that is molar mass P over what? RT. Equation waiting 4. Equation 4. So this is the final equation. Now from this equation you've gotten, how would you now interpret Graham's law of diffusion? How would you interpret Graham's law of diffusion? I can interpret Graham's law of diffusion by saying that the density is directly proportional to the molecular mass. Now from this law that we have, from this formula we've deduced, we can say that density is what? Directly proportional to molecular what? Mass. That is from the formula, but the law itself said that the density, that is the square root of the molar mass, that is to the square root, please, to the square root of what? Molar mass. That means big letter what? M. From the law, we said that rates of diffusion of gases is also very proportional to the word density. It means that R is it directly inverse proportional to what? Density. So please, in conclusion, we say that the rate of diffusion of gas is inverse proportional to the molecular mass, that is 1 over square root of m. Normally from this place, the density here is directly proportional to molecular mass, right? To its molecular mass. But if we want to rephrase it based on what was said, we can say now that the rate is inversely proportional to the square root of its molecular mass. The rate is also inverse proportional to what? The square root of it, what? Vapor density. So these are the two things that can be coined from Graham's law of what? Diffusion. So we are done with the 3 laws. I think the last law is the law of effusion. The law of effusion was also stated by Thomas Graham. The word effusion means the passage of a substance through a small hole, and this hole is called pinhole. All right. So this law states that at constant temperature and pressure, the movement of a substance through an orifice, all right, I'll take it. Effusion means the passage of substance through a small hole called pinhole. This law states that at constant temperature and pressure, the movement of gases through an orifice is both inversely proportional to the molecular mass and what? As the square root of molecular mass and square root of vapor density, which means that effusion is expressed as the rate is 1 over the square root of density, then the square root of what? Molecular mass, molecular weighting mass, molecular mass. Now, if I want to relate rates and molecular mass of two entities, I can say rate A over rate B is equals the square root of molecular mass of B over the molecular mass of what? A. So that if I cross multiply, I'll have this, I'll have this. So at this point, we call it a day. Thanks for watching. Do have a wonderful day. Please subscribe so that when I upload the videos on calculations on this topic, you'll be notified by YouTube. Do have a wonderful day.